Swayam Prabha. Digital India. Educated India.
Hello, welcome back. So, today's class will continue discussing on the cross coupling reaction, or so to speak the carbon-carbon bond formation reaction. In the last class, we have seen the generalized mechanism for the carbon-carbon bond formation reaction. The name reactions, there are plenty of it in this domain, so to speak. Lithium and magnesium as a transmetallitic reagent would be called Kumada reaction. Boron as a starting material or organoboron reagent, if it is used for these carbon-carbon bond formation reaction, that is usually called the Suzuki reaction. If it is tin, that is Stille reaction. If it is silicon, that is the Hiyama reaction, or if it is as we said zinc, it is Nigisi reaction, right. So, all these reactions are the one which forms the basis for the difficult carbon-carbon bond formation reaction that one would like to achieve. The generalized mechanism that we have discussed, we have incorporated palladium 0 to 2 plus catalytic cycle. Now, as we also discussed that mechanism is not going to be the case for everyone or every metal. Sometimes it is radical reactions, most importantly sometime when we do have the nickel as a catalyst, then we have a radical reaction in place. Today we will see the transmetallation reaction little bit, how transmetallation reaction is occurring. We have discussed the oxidative addition as the first step, then the transmetallation, then the reductive elimination for the process. Today we will just briefly look at the transmetallation process and then start discussing mainly about the Kumada coupling in short. Let us look at the transmetallation process. Transmetallation, this is often happening via sigma bond metathesis, which is interesting, quite interesting. I would say often via sigma bond metathesis. What you have here is palladium X and the transmetallitic reagent or Rm, right, R prime M for example. Sigma bond metathesis usually will give rise to the palladium metathesis, palladium X and R prime. This is the 4 central mechanism or sigma bond metathesis mechanism that would be involved in the transition state, and we have palladium R prime and exchange of partner Xm. Now, substituent effects usually for example, oxidative addition, if we are looking at oxidative addition, substitution has a lot of importance in the process. Overall, if you look at if we have an electron rich substituent on organohalide, we have a slower reaction. If we have a sterically bulky substituent in the organohalide reagent, then also we have a very slow reaction. On the other hand, if the leaving group is iodo, that is more facile over bromo than chloro, and the reactivity pattern of the aryl halides are also quite interesting, and their electronic properties would matter a lot during the processes. Let us look at again the properties of organohalide that would be important for these cross coupling reactions. Substituent effect, for ARX organohalide reagent, right. Well, more electron rich aryl will be having a slower reaction. Okay. The opposite also true, definitely true. Electron deficient aryl halide will be giving faster reaction. More hindered the reaction is sterically it is challenged reactions are, so then we have a slower reaction. And effect of X, that is organohalide, what type of halide you have, effect of X is usually iodo is more reactive than bromo, which is similar as OTF, and then the chloro. Okay. So, this is an interesting reaction pattern, and we would say that reactivity pattern can be consistent or is consistent with the oxidative addition at the organohalide reagent. Okay. Let us try to look at each of these carbon-carbon bond formation reaction in little bit more detail. We will try to give a overview, and then we will discuss few of these things in more detail. Today we will start discussing about the Kumada coupling. Again, Kumada coupling is the one where organolithium or organomagnesium reagent is used for the carbon-carbon bond formation reaction. Let us look at the Kumada coupling in little bit detail, and then some of the example we would like to discuss as well. So, Kumada coupling, it is discovered in 1972. Okay. That is one of the golden era, I would say. RX are lithium and or RMGBr, of course, or RMGBr, any of these in presence of palladium catalyst would give you R prime. Okay, this is the R prime, one of those R and R prime will be utilized. The common catalyst that is used are the one which is usually known as palladium tetrakis or palladium tetrakis triphenyl phosphine, that is usually referred as palladium tetrakis, or we do have DPPF as the reagent as well, or the ligand for palladium, and we do have PPH2 DPPF is PPH2 reagent. This is the ligand, and palladium chloride is used for this purpose. Also we can have DPP as the ligand for the palladium, and we do have palladium chloride, these different palladium chloride that can be used for these processes. Now, for the Kumada coupling reaction or for any of these carbon-carbon bond formation reaction, we know that usually although we need a palladium 0 as a catalyst, but we start with palladium 2, that is quite interesting. So, what is usually thought or has been proven by now that initial starting material although is palladium 2 is generating palladium 0 very rapidly under the reaction condition. So, the real active species is palladium 0 that is undergoing oxidative addition with aryl halide or organohalide reagent, but the starting material is, let us say for example, palladium chloride or palladium acetate, these are palladium 2. So, there must be a very good mechanism by which these palladium 2 reagents are forming these palladium 0 reagent. But what is wrong with palladium 0 as a starting material? Well, usually palladium 0 itself cannot be very you cannot buy it from the commercial source, except when you have a very good stabilizing ligand with the palladium 0. For example, palladium DBA, PD2 DBA3 or palladium DBA or other palladium 0 reagent, where you have ligand associated with it by virtue of the ligand being very good donor, displacing that ligand with your desired ligand, that is usually a phosphine ligand, becomes challenging, or it competes with the phosphine binding. So, therefore, extra ligand you usually do not want to have during your palladium catalysis that can hamper your real catalytic cycle. So, the idea usually that is found to be very general is you start with palladium 2, under the reaction condition in situ it will form palladium 0 rather rapidly. Some cases when it is slow then there could be a problem, but otherwise palladium 2 to palladium 0 formation happens in presence of often the starting material that you need to use for the carbon-carbon bond formation reactions. We will discuss one of the method by which the palladium 2 is converted to palladium 0 in situ, therefore, palladium 2 is used as the material for these cross coupling reactions. Okay. Generation of palladium 0 from palladium 2. Of course, there exist several mechanisms by which this happens. This is just one of the mechanism. A specific case, palladium chloride, let us say we are using, palladium is in +2 oxidation state, that is not of our interest. We are interested in palladium 0. So, what happens if you are doing the Kumada coupling with organolithium reagent, if you are using let us say 5% palladium, so nearly 10% organolithium reagent will be required. This is used, this is where we see that little bit excess of organolithium is used, let us say 1.1 equivalent, that 0.1 equivalent will be utilized for palladium 2 to palladium 0 formation. Okay. And often we have palladium to R and R prime, that is what is expected. You know, from here let us say this you have R prime, from here you will get R prime and R prime. This is a side product and it is forming in very less amount, and in the process what you get Ln palladium 0, that is the one which you are interested in. So, what you have seen right now is palladium 2 as a starting material is converted to palladium 0 in presence of sacrificial organolithium reagent. Organolithium reagent in any way you are going to use for your Kumada coupling reagent, some part of those organolithium reagent will be utilized for palladium 0 formation. That is usually true for almost every carbon-carbon bond formation reaction by utilizing this sort of cross coupling reaction. One of the reagent will be helping sometime base, combination of base, little bit of oxygen or air or moisture, sometime the other boron reagent and so on. In any way, one way or the other, one need to form palladium 2 to palladium 0, because palladium 0 is the one you are interested in, that is the real active site, active species. You do not want palladium 0 to be directly used from the market, because palladium 0 is stabilized with a ligand which is usually difficult to get rid of from the palladium 0 site. Okay. Now, that is one of the method. Let us look at some of the example of these Kumada coupling reactions. One of the example that is easier for this styrenyl bromide, for example, N-butyl magnesium chloride. So, if you are using catalytic amount of palladium DPPF chloride, you get 90% yield of the product which you might be interested in N-butyl in over here. This is trans geometry both in the starting material, both in the product. That is very interesting. Both the starting material and the product will have the same geometry. That is one of the key factor one would look for. The starting material and the product formation, if you have a trans olefin, alkynyl halide, if you are starting with, if it is having trans geometry, will you get trans or a mixture of cis and trans or cis? The answer for the Kumada coupling, for example, it retains the geometry. So, if you start with trans, you get the trans. Well, to demonstrate this point, even one can utilize a mixture of cis and trans, and selectively the one that is more reactive will be giving the product first, the other one which is less reactive can give the product next. Let us look at one of those examples where we have two starting material, one is in trans geometry, the another one is in cis geometry, and then you are reacting that with the under the Kumada coupling condition, and then what is the product formation during these processes. So, we are looking at E versus Z or Z selectivity, reactivity pattern. The starting material we are taking first is the one where you have a trans geometry and the corresponding other one is there. Let us say you take 67 is to 33, that means 2 is to 1 category, you are taking one equivalent of it. Total you have these two reagent in one equivalent, but one of them is 67 and another is 33 equivalent, or 0.67 and 0.33 equivalent. And if you are reacting this with 0.66 equivalent, that means if it is 2 is to 1, you are taking 2 equivalent of N-propyl magnesium bromide. So, that means you are going to do the Kumada coupling in presence of the palladium catalyst, specifically let us say DPPF dichloride if you are taking. Now, what is observed in these cases is you get, since you have 2 is to 1 and 2 equivalent of the organomagnesium reagent, and you get the one of the product only, selectively you get the trans product that is more reactive. So, 2 equivalent reacting with, or 2 is to 1, the 0.66 equivalent or 0.67 equivalent reacting with 0.66 equivalent of N-propyl magnesium bromide to selectively give this product in trans geometry, and this starting material is selectively 100% converted to the product. This reagent, although similar, only it is the cis one, is not reacting at all for the product formation reaction. Now, that is quite interesting, because even when you have a mixture, still you can fish out the one you want based on their reactivity. Okay. So, the geometry is geometry is retained during the Kumada coupling reactions. It is, although it is a mixture of trans and cis, there is no mixture of product formation as long as you have the controlled delivery of the organomagnesium reagent or Grignard reagent if you are using in a very selected amount. Now, this Kumada coupling is very good, right? As you see that it can maintain the stereochemistry. It's a very good approach, but the problem, well, one would expect that you are using organolithium reagent, or you are using the Grignard reagent as the coupling partner. These reagents are very reactive, and they are notoriously reactive towards functional group. So, therefore, functional group compatibility is an issue. That is the major drawbacks of the Kumada coupling, although it is a great reaction, but if you have too many functional group, ester, ketone, different other aldehyde and other sensitive cyanide, other sensitive functional group, you could run into danger, because under the reaction condition, those functional group can also get affected by this organolithium or magnesium or the Grignard reagent that you are using. So, one has to be careful about the Kumada coupling. Okay. Now, next we would like to briefly discuss about the Suzuki reaction. See, each of these reactions we can discuss hours after hours, because there are a lot of advances being made, a lot of problems being addressed, first of all identified and then addressed, and these are truly why the organometallic chemistry is considered very highly in modern synthetic chemistry. We are trying to keep it brief. Maybe we will come back to these discussions once again in greater detail. Let us look at briefly the Suzuki reaction. Suzuki reaction, I think, is one of the most promising and one of the most popular reaction at this point of time, and it is very truly perhaps one of the most referred chemistry by chemist and non-chemist alike. Okay. Let us look at the Suzuki reactions. So, the reagent what is used, organohalide once again, and organoboron reagent or boron reagent BY2. Now, palladium catalyst is used, sometime also nickel, sometime nickel. Okay. Additive, stoichiometric additive are used, usually stoichiometric additive are used, palladium catalyzed reaction stoichiometric used, and the you form R prime. If it is a Br2, that means trialkyl borane, that can also be used as the sufficient or suitable coupling partner for the Suzuki reaction. If you have a boronic acid, okay, this is boronic acid, that is one of the most famous one that is used. If you have boronic ester, that can also be a suitable partner for this sort of reaction, boronic ester. If you have aryl trifluoroborate, okay, usually called molandarets, trifluoroborate, that can be also used as the coupling partner for these reactions. So, there are many different organoborane reagents that can be used for the Suzuki coupling reaction, but invariably usually they end up giving the product quite nicely. How one would get the transmetalliting reagent in presence or transmetallation in presence of those organoboron reagent is one of the areas people have studied, and it is now quite well understood. You need a base, you need a nucleophile for this organoboron reagent to be participating into the transmetallation step. Once again, oxidative addition will be the first step, then transmetallation and then reductive elimination for these carbon-carbon bond formation reactions. Let us look at the transmetallation utilizing organoboron as the material and how they might will be involved during the processes. So, basic additive is usually required. The basic additive could be your sodium hydroxide, sodium methoxide, fluoride, etc. These are called usually nucleophile, let us say we can call them, and it is reacting with organoboron reagent, for example organoboronic acid. Organoboronic acid reacting with nucleophile to give RB, this nucleophile hydroxo 2. Overall, this is more reactive in transmetallation. The resultant species becomes more reactive in transmetallation than compared to this organoboronic acid or any organoboron reagent that might be used for the process. Now, that is quite interesting, because boron usually itself is not that much good for transmetallation, but when you have a nucleophile such as base, sodium hydroxide, sodium methoxide, fluoride, anything you want, once you add that, then it becomes a much better transmetallating reagent by which this transmetallation reaction can proceed, and therefore product formation can be viable. What is also important to understand that these reactions are quite useful, not only a aryl and aryl coupling, which is usually the case or usually most widely studied, or Suzuki reaction where you have, let us say, aryl halide reacting with another aryl boronic acid to give you aryl, that means biaryl fragment. Okay, that is, I think, is quite well understood or quite well explored. The one which are little bit problematic could be the alkynyl halide one, where you have this alkynyl halide reacting quite efficiently for this boronic acid reaction as well, or the Suzuki reaction. Let us try to look at one such example where as sp2 carbon, of course, alkynyl halide is reacted with alkynyl boronic acid or boron reagent to give you the carbon-carbon bond formation between the two alkynyl centers. Let us look at the examples. We have, let us say, protected alcohol and boron reagent, and we have this alkynyl halide, for example, over here, to give you these. Again, both the partners are sp2 carbon center, and these are alkynyl. These are considered as the coupling between this sp2 and this sp2, where it is alkynyl, and this is also a conjugated one along with the alcohol. You have allyl alcohol as well, and over here allyl alcohol protected as well. From here on, you can get, in presence of palladium tetrakis, you can get the desired product. That is quite amazing, I would say, because the overall the product formation. So, this is your new bond, and of course, this is E geometry, and this was the Z geometry over here. As from the starting material, the same geometry is retained. Of course, rest of the things can be as it is. Okay. So, what you see in this particular product, what is most important for these two particular starting material is these are having a particular geometry both on the halide and the boronic acid reagent. But irrespective of the geometry, you see in the product formation both the geometry are retained. Okay. As they are in the starting material, you get the same thing in the product formation. That I think is quite amazing, and you can perhaps take almost at this point almost any sp2 bond formation can be done by almost any. I mean, not definitely everything, there are existing limitations are plenty, but most often what you may need, this is the reaction perhaps to go for, and the geometry of the starting material could be retained. So, with this, for today's class, we would like to summarize that we have discussed the Kumada coupling reaction with plenty of with some example, and also we started discussing the Suzuki reaction with some very attractive example. We did not discuss way too many of the other biaryl coupling formation, because those are very well known. The one which are more difficult are the one where alkynyl halide and alkynyl your organoborane reagent are involved. Of course, sp3 carbon center could be another approach or another difficult coupling partner. Indeed, those can also be done by this Suzuki reaction. Anyway, but the problem with the Kumada reaction, as we discussed, it is a very good reaction. Geometry of the starting materials can be retained, but since we are using for Kumada reaction organolithium or organomagnesium reagent, therefore, there is a danger of having the sensitive functional group being attacked under the reaction. So, that cannot be, Kumada coupling cannot be a reliable reaction under a condition where many functional group are there. On the other hand, Suzuki reaction, what is important is it is usually can tolerate quite wide variety of functional group, even the geometry of the starting materials retained, and a lot of other beneficial features we will be discussing in the next class, and maybe we will come back again in a much broader way to discuss more of the efficiency and the drawbacks of these reaction individually. Till then, I will see you in the next class. Keep studying this carbon-carbon bond formation reaction. Bye bye.